Hello and welcome to the third video in our lecture on digital envelopes and pseudo-random number generation. So in this video, we want to study what it means for a number to be random. Actually, if you're only given a single number, say the number 5, it's impossible to determine if that number is random, unless you know how that number was generated or according to what process it was obtained. So instead of looking at a single number and asking if it's random, we're going to look at a sequence of numbers and then ask if that sequence is random. So does it mean for a sequence of numbers to be random? Well, basically what it means is that if you were to look at a sequence, there would be no way for you to predict what each number is going to be other than by guessing, by using chance. So more precisely, there are two criteria that we're going to use to assess if a sequence of numbers is random. First is called uniform distribution. So we say that a sequence of numbers exhibits a uniform distribution if every possible value that could appear in that sequence does appear in a sequence with a probability that's about equal to the probability of all the other values that could appear. So for example, if we're looking at a sequence of numbers and the only two possible values are zeros and ones, okay? So this is a random bit string, and you're asking if this sequence exhibits a uniform distribution. There's a very easy way to check since there's only two possible values, zeros and ones, and they should have the same probability of occurrence. Then what you have to do is simply count the number of zeros and the number of ones, and these should be approximately equal. In other words, when this sequence was generated, every bit in that sequence had a 50-50 chance of being a 0 or a 1. So if you run this process long enough, and if you get a long enough sequence, when you count the numbers of zeros and 1, they should be approximately equal. And in fact, the longer the sequence, the closer to a 50-50 split you're going to get. So this is a uniform distribution. Another property that is very important is called independence. And so we say that a sequence of numbers is independent if no value in the sequence can be inferred based on knowledge of any other part of the sequence. So for example, if knowing this initial part of the sequence and these couple bits over here allowed you to predict for sure what this bit would be, then these values would not be independent. So this is a very important property that says that you cannot predict the value of any bit based on the knowledge of any other subsequence of bits, including every other bit in the sequence doesn't allow you to guess the next one. So let's take a concrete example to see why this notion of independence is important. So let's say we have a server that generates bit strings to be used as keys for a particular set of users or processes. So we have a key generated for Alice, and one for Bob, one for Charlie, and one for Dave. And I'm going to write down quote unquote random bit strings that are very short. So they're not really real possible keys here, but just for the sake of illustration. So let's say that this server generates those keys randomly. Well, if those sequences are random, then they should be independent. And so what that means is even though those keys initially are supposed to be known only to their user, so unless they decide to share them later, only Alice knows this bit string and only Bob knows this bit string and so on and so forth. So if these sequences of bits were not independent, that means based on the knowledge of some bits, that person would be able to infer maybe the value of some other bit. And in fact, the more knowledge would be known if the sequences were not independent, the more bits you would know, then the higher the easier it would be for you to predict some other bits. And this is definitely something that we do not want in such a scenario, because that means if those three users, for example, decided to get together and share their keys, now they would all three know the totality of those three sequences, and maybe if the sequence were not independent, they would be able to use that knowledge to infer the bit string for a fourth user. So they could collude and basically attack that user. So we do want to have this property of independence if possible. Now, how do we check for these properties? It turns out for uniform distribution, the checks exist and they are pretty easy. Remember when we're checking for uniform distribution here, all we had to do was to count the number of zeros and the number of ones. Now, of course, things are not that easy because you still have to do some testing for statistical significance and so on. But the theory of these tests is well developed and well known. So testing for uniform distribution is relatively simple. Unfortunately, it's not the same for independence. So it turns out there are no tests that will tell you for sure if a sequence is independent. On the other hand, we do have some tests that check the opposite for non-independence. That is, it's possible to find a test T1 that if you give it a sequence, it will tell you, yes, this sequence is actually not independent. So it can prove the negative of independence. And the fact is there are several, quite a few of these tests that are known, T1, T2, TK, say. So one way to actually establish that a sequence has this independence property, you cannot just prove it for sure. But what you could do is you can feed your sequence to one of those tests. And if that test gives you the answer no, that means it was not able to prove that the sequence was not independent. Then that means the sequence could be independent. You don't know for sure, but it could be. So then what you do is you take this same sequence and you feed it to a second such test. And if that test answers no, well, that means that test was not able to prove that the sequence was not independent. So it could still be dependent. And so what happens is if you do a sequence of this test that is long enough and all of these tests answer no, that means after a lot of effort, you were not able to prove that the sequence was not independent. Well, this is pretty strong evidence that the sequence is independent. It's not a proof, but maybe it will give you enough confidence that you can move on and start using those sequences. So here is the quick summary. So these properties are two properties that we're interested in when we're looking for random sequences of numbers. So the good news is that this sequence is easy to test for, and the bad news is that this sequence is not easy to test for. And there's another bad news, which is that this sequence by itself is not sufficient to determine randomness. So what I mean by that is it's very easy to find sequences that exhibit this property but are not random. So for example, if I show you the beginning of a sequence and I say, here is the beginning. So can you predict, knowing this beginning of the sequence, what the next bit is going to be? And most people would look at this and say, well, yeah, it's probably going to be a 0. Even though that sequence does exhibit uniform distribution because the number of zeros and ones is actually exactly equal. So the bottom line is that this property is easy to test for, but is not sufficient in and of itself to prove randomness. And even though this property is very strong, if you can prove it, it's actually very hard to prove it. So we're going to therefore use a third property called unpredictability. So in the previous example of the server that was generating keys and in similar applications for cryptography, we do not really need to prove that the sequence is either independent or even just statistically random. Really, the one thing that we do want to know is that this sequence of bits is unpredictable. Okay? So the reason for that, again, is because in the case of the server before, by knowing all of the previous bits in the sequences of the keys previously generated, if there is no predictability, that will not allow you to guess or figure out what the next key for Dave is going to be. So here it's important to keep straight the different concepts. So first we're going to start with the concept of randomness or true randomness. So let's say we have a truly random sequence of numbers. Then by definition, this sequence exhibits independence, because if the sequence was not independent and some of the bits depended on some other bits, then there would not be true randomness in that sequence. And then once you have independence, which is a very strong property, independence of the bits also implies unpredictability. Because the only way you can predict the next value, for example, would be to use some relationship or some dependence between that bit and the other ones. So true randomness um, implies independence, and independence implies unpredictability. And basically, what we're saying is that in applications for cryptography, we're perfectly happy to have a completely unpredictable sequence if we can get one. So we don't really have to use a truly random sequence, and we don't even have to worry about testing for independence or finding or using an independent sequence. We are just happy if we can find a completely unpredictable sequence. And that is the key, because, well, as we'll discuss later, true randomness is not easy to harness. So instead, what we're going to do is we're going to focus on predictable sequences, and we're going to be able to generate those using some algorithm. Now, of course, this looks a little bit contradictory, because how can an algorithm, which by definition is deterministic, how can it produce a sequence of numbers that is random? Well, the answer is that it cannot. Okay. But again, we are not really looking for true randomness or true independence of the values within the sequence. We're going to be satisfied by using sequences that are simply unpredictable, because unpredictability by itself is enough to thwart an attacker who would want to use the known sequence to predict the upcoming numbers. So the topic of the next video is going to be how to use deterministic algorithms to obtain random enough, quote unquote, sequences of bits.